Hello, welcome back. This is journal number 42. I'm going to put your name first and last, please. Click the button for whatever period you're in. Excuse me. All right, so the question is to describe a polar molecular compound, give an example. Describe a non-polar molecular compound, give an example. And then what's soap got to do with it? What's soap got to do? Yeah. Anyway, all right, so a polar molecule is one that has poles, like the Earth has a north and a south pole, or a magnet has north and south poles, right? So it's meaning that you've got opposite charges. So a polar molecular compound has opposite charges that attract to each other. It is a slight electrical charge due to the larger atom pulling harder on the shared electrons. I like to think about it like this. So let's pretend we're going to have a tug of war game, and we're going to put the 20 beefiest senior football players versus the 20 scrawniest seventh graders. Who's going to win? Like, easy, right? Like, you're not going to. What if it was the 20 biggest football players that were seniors versus the 20 biggest football players that are juniors? Not that there's that many football players at Nottaway, but in other places, we got them all together. Anyway, the point is, that's going to be a lot harder to predict. And in fact, the juniors might win, because once you get to that age of, being around 17, 18 years old, there's not a whole lot of difference between a 16-year-old and a 17-year-old for the most part, or the 17 and 18 for the most part. And especially if they're already playing football and working out and all that stuff, there's no guarantee that who's going to win. So this is what happens in these compounds. So in a polar compound, that's like the seventh graders versus the seniors, where it obviously the one is going to pull way harder and win every time. So it pulls those shared electrons closer and therefore becomes negatively charged, only slightly, but negatively charged. And then the atom that lost the electron, well, didn't lose it, but it's not pulling as hard on the shared electrons. It has a slight positive charge. So this is why water is sticky, because hydrogens have a slight positive charge and the oxygen has a slight negative charge from those shared electrons. Now, it's not as strong as in ions. It's like, the refrigerator magnets that are so cheap that every time you shut the refrigerator door, they slide down it, right? That's the kind of bond we're talking about here. Ions are like the neodymium magnets that get your finger out of the way or it'll smush, the apple smushing magnets. That's an ionic bond. It's very strong. It is attractive, but weak, okay? All right, and then to give an example, well, I just gave an example. Main one I want you to know is water. Then anything that has something in hydrogen is going to be a polar compound. So methane is CH4. Ammonia is NH3. So both of those are going to be polar because we're talking about a larger atom pulling harder on those shared electrons because the hydrogen is so little. All right, then question 2 is to describe a nonpolar. So in a nonpolar molecular compound, the shared electrons are being pulled on evenly. Nobody's pulling harder on the other one. It's like the seniors versus the juniors, where, yeah, they're a little different in age, but they're about the same size. So it's not so easy to say one's going to beat the other one. So anything where you have the same atom, so N2, F2, O2, Cl2, any of those things that are like fluorine gas, nitrogen gas, oxygen gas, carbon dioxide is a nonpolar compound because it has the carbon in the middle and then oxygen on either side, and they're evenly pulling on those shared electrons. So it's a nonpolar compound. So it has it does not. Well, let's see. It pulls evenly. That's what we want. Both atoms. Here we go. Both atoms. Sweet. If you think about it in a minute. Words. Both atoms pull equally on the shared electrons. electrons, no electrical charges. So an example, well, oil is the main one that we talked about in class. Oil is less dense than water, and that's why it floats on top, but then they also don't mix very well because one's polar and one's nonpolar. Then also, like I said, any of those things that are themselves. So nitrogen gas, oxygen gas, all those things. And then the last question is, what soap got to do with it? So soap is a long, complicated molecule. It's got a polar end and a nonpolar end. The polar end bonds with the water. The nonpolar end bonds with the oil and the dirt and brings it in together into the lather that you then rinse away. So soap, what soap got to do with it? Well, soap's both. So soap is a long, complicated molecule with a polar and non-polar end. The polar end attaches to the water, non-polar to the oil/dirt, bringing them together to then rinse away. All right, hit submit. That's it. Have a lovely day. Make good decisions. Bye.